Start recording so I don't forget. And so if you guys followed the last video, if you haven't watched it, you'll want to watch it because it's gonna give you the numbers you need to actually go through this troubleshooting stuff later when we practice it. But if you watch the last video, that helps you determine whether or not something is normal in a refrigeration system. AC mostly, right? We're talking mostly comfort cooling here. What I want to do tonight is talk about charging and stuff like that pretty briefly, and then I want to talk about different pressures you might see in a system, not actual pressures and things like that. We're going to work on that a little bit next class. But for this class, we're just going to say, what if it's high? What if it's low? What kind of issues might we be having? Things like that. And then what we go over tonight, at the end of the class, I will throw it in Google Classroom and make it a handout so that you can download the files and take a look at them. And if anybody happens to notice something that doesn't look right, like I put something in there and it doesn't seem like it's correct, let me know. But for the most part, it should all be pretty accurate. But I was trying to transcribe some stuff, and I switched on how I put stuff together, so I might have put low where I should have put high somewhere or something like that. But hopefully as we're going through it tonight, we'll catch that stuff if I did do that. So most of this information comes from like Carrier and Trains, and even in the back of an Ari Michael catalog, you've got some troubleshooting stuff on refrigeration circuits. So I kind of put some of that stuff together and made my own deal with it so that I could show it to you guys. But first, what I have up now, superheat charging chart, right? This is a generic. What's that? Yeah, no, I already started it, so we're good. But anyway, so let's start at the beginning, right? Before you start troubleshooting, say everything else looks good, but you're having some kind of circuit issue. So, electrically everything works, because if you guys do a lot of troubleshooting, you'll find out that most of our issues are mechanical, right? Most of our issues are electrical. So 9 times out of 10, you're going to be troubleshooting electrical issues, and we'll talk about troubleshooting electrical components later. But if you determine that you do have a issue in the AC system and you're trying to figure it out, first thing you want to do is make sure everything looks clean and it looks like your charge is good, at least halfway. Obviously, if you got an undercharge, that's part of what we're going to talk about. But you want to make sure everything looks clean. You don't want to be troubleshooting refrigeration issues and have a problem on top of a dirty coil or something like that. We'll talk about what dirty coils look like. But if you look at the coils, or you look at the fan motor, or you look at the fan motor. If you look at the coils, you look at the fan wheel, or you look at the filter, and that stuff's dirty, you don't want to try and keep going trying to find out a problem when you've got other things. You want to try and narrow it down to, I have one issue in the refrigeration circuit that I need to figure out what's going on. If you're, like I said, if you're trying to troubleshoot it on top of those things, you're just going to have a bad day. If we go through this, if after we go through this stuff down the road, you're trying to troubleshoot an issue and you just can't seem to figure it out, then make sure the charge is good. How you make sure the charge is good? Just go ahead, pull out the charge into a recovery cylinder, and if you don't think there's any non-condensables or whatever in it, just weigh it back in. If you suspect non-condensables, then you should test for non-condensables, and then obviously start with a fresh charge. But if you absolutely cannot figure out what the heck's going on, then just tell the customer, if you got to, I got to clean the coils and I've got to weigh this charge in so I can figure this out. because they can get really messed up when you're dealing with an undercharge, with a dirty evap coil, and an inefficient compressor or something like that. You start compounding issues on top of each other, and that's when you're going to be scratching your head for 2 or 3 hours. So if you are having trouble figuring it out and nothing seems to match what you see on these charts or anything like that, and just clean the coils, pull out the charge, weigh it back in. I don't know how many of you guys run service and stuff. I can't remember. I gotta go back and look at the personal info I had you pull, but I know you get, like, it seems anyway, in my experience, it's like 50-50 guys that actually carry tanks and a recovery machine and ones that don't. And some guys think it's a big hassle to pull out that recovery machine and put it into a tank. It's not that hard most of the time. It doesn't take as long as you think to just pull out the charge and weigh it back in. If you weigh the charge in, you know the charge is good, you know you got clean coils, it's easy to start from there, because now you've eliminated a bunch of common issues that you might have to deal with. So that's pro tip number 1. If it's just a complete head scratcher, go ahead and make sure coils are clean, weigh the charge in, start fresh, and you know, hey, this is what I'm working with. You don't have to pull everything out and evacuate it, especially, like I said, if you don't think there's non-condensables in there and it looks good, then just pull out enough that you're close to zero and you have a good idea of where the charge is at, weigh that back in, and get it close enough that the charge shouldn't be what's screwing you up. Does that make sense? All right. So once you're at that point, you either are dealing with a single problem. Well, no, I lie. We're going to charging next. So charging chart. Let's look over this first real quick. I wanted to do charging charts first just so that it's covered, because it doesn't really fit in anywhere else anyway. This, like I said, I'll give you guys a copy of this. This is superheat charging chart for fixed orifice metering. You'll see a few different ones. I might make a table too, or you can download tables online where they'll give you like indoor temperature, outdoor temperature, and you can just kind of line up the columns and rows that way and see where your superheat should be if you're dealing with the fixed orifice. I always kind of like Train's one, so this is my rendition of Train's superheat charging chart. Basically, you've got your superheat. Matter of fact, let me see if I can zoom out a hair real quick, or zoom back in a hair. All right. I got a window bugging me. All right. So, what you're gonna have here is you got outdoor temperature on the bottom. You have superheat on the side. So if you're charging a fixed orifice, you'll find your outdoor temperature, and then you'll find your indoor temperature. Notice we got two numbers here. The diagonal lines are indoor dry bulb and wet bulb temps. So the first number is dry bulb, second number is wet bulb. For 50% humidity, you can use dry bulb. Other than 50%, using wet bulb is going to be more accurate for charging superheat. I generally say as long as I'm somewhere between 40 and 60, and here in our area we're usually going to be closer between 50 and 60. As long as the humidity is not crazy inside the house, then you're fine using dry bulb. But if you can get a psychrometer in there and actually check wet bulb, or calculate wet bulb using the relative humidity inside the house or inside the return duct, then using that wet bulb number will get you much closer to where you need to be. But just pick your temp, follow the chart down to your outdoor temp, and then you read your superheat to the right. So if it's 90 degrees outside and it's 80 degrees in the house, all right, we'll follow this thing down till we get to 80 degrees in the house right here, right? 90 degrees. Oh, sorry, 90 degrees in the house. What are we doing? What did I say? We're going to do 90 degrees in the house, and 80 degrees outside. So say the system hasn't been working all day, right? System hasn't been working all day. It was almost 100 degrees outside. House got up to 90 degrees, but the outdoor temp's starting to drop. So it's actually 90 degrees outside, or inside, 90 degrees inside, 80 degrees outside. So you go 90 degrees, line that up with 80 degrees right here. So that's the outdoor temp. This is your indoor temp. You follow it over, you're going to have like 28 degrees of superheat. It gets real crazy. You can see your superheats can get super high if it's cool outside and it's warm inside. So it's something to keep in mind. If it starts cooling off, if you're servicing a system in the evening when it starts cooling off but it's still really warm in a house, then your superheat's going to be practically through the roof. So that's when a lot of overcharges happen. Even good tech sometimes will overcharge on a fixed orifice when it's cooler outside and warmer inside. But other than that, it's fairly self-explanatory. If we're 80 degrees outside, 75 degrees inside, you're just over 10 degrees of superheat. Basically, you're looking for 10 or 11. So this is just a generic chart. Keep in mind, if you're working on a system, it's always better to use their chart and make sure their orifice is matched and everything's good. But if you don't have their chart, then this is a generic chart that'll get you close enough to make sure everything's working good if you're using a standard fixed orifice. Is there any questions on this? We're going to look at another example down below, but then after that, it's basically just using a superheat chart. If you ever seen graphs like this, some of the commercial systems are set up with graphs like this. A lot of residential systems will have the table. I don't know why I've always liked this graph, but this is always the one I use generic. So you guys will have that. Fixed orifices obviously are becoming less common, but they're still around. You still got to work on them. So when you run into them, this is usually what I use if I don't have their chart available. Remember, the closer you are to design conditions, the easier it is to get a good charge in. The more normal all those numbers are going to work. But, sometimes you're charging when it's hot. Happens. All right. Superheat. Other charging notes. I guess I can pull down some more. All right. Other charging notes. Superheat plus or minus 5 degrees is generally acceptable. With modern gauges and stuff, there's really no reason to not be as close as possible to what you think your target number should be or what your target number is. But plus or minus 5 on superheat is generally fine. That's kind of the range they'll generally give you and say it's okay. So plus or minus 5. If you're plus or minus 5 degrees on superheat, you think you need to charge, that's fine. Just make sure everything else is in good shape before you add that charge. If you can hit it dead perfect, hit it dead perfect. But if you've got other things you need to work out, if your superheat is plus or minus 5, just deal with other issues before you start messing with the charge, because that's going to skew everything. But remember, you always have to maintain 10 to 20 degrees absolute minimum, and usually it's going to be 20 to 30. But you need to have superheat 6 to 12 inches from the compressor to avoid slugging. So never add charge. You see the line right here, right? Do not charge if below 5 degrees superheat. If you see less than 5 degrees superheat, it might be normal. Okay, you can see these lines start to dip down here at certain temps. There will be times with a fixed orifice that you're kind of low on superheat, and there's not a whole lot you can do about it. That's one of the downsides to a fixed orifice. But if you're below 5 degrees superheat, don't add no charge. All right, there's no reason to charge it until you can get slightly more normal conditions and see where your superheat should be. So just keep that in mind. As I think I stated in the last class on what is normal, but I'll repeat it again. Superheat is like your most important number. It keeps your compressor healthy. So if your superheat's way out of whack, figure out how to fix it. but if it's getting low, we don't want to cause any mechanical failures. Scroll compressors are a little more able to deal with a little bit of liquid getting in there and stuff like that. Most compressor designs, even if you've got zero superheat to the compressor itself, by the time it goes across the motor and everything in that compressor, you usually have something. But don't let it get too low, and obviously too high, you're just going to burn it up. So you want to keep superheat as close as possible to where it should be, but don't charge it. And if you ever don't have superheat, if you got compressor sweating, or you don't have superheat 6 to 12 inches from the compressor, you should probably be pulling out charge until you figure out what's going on. But diagnose everything else you can first. But yeah, if you got sweating, figure out why you got it. It's probably not the charge, but it could be overcharged so bad that it's got no superheat, and that's not a good thing. TXVs are what is a lot more common, TXVs and EEVs these days. For residential TXV systems, I'm sure you guys know, but it doesn't hurt repeating it. 10 degrees subcooling is generally fine. Just start out 10 degrees subcooling. Systems used to be like 7. I'd see some that were 7 and some that were 9 and some that were 12. I think most of the ones I've put in for the last couple years have always just said 10. 10 degrees subcooling is usually fine. Plus or minus 3 is generally fine. I have seen systems with 10, 11 degrees of superheat where if you got a sight glass, you'll still have some flash gas in the sight glass because it's a longer line set or something like that. So you may need to push subcooling a little bit so that you've got a solid column of liquid to the metering device. But in general, if you're between 7 and 13, it should work as intended. And if you've got issues with the system working as intended with a subcooling of plus or minus, a subcooling of 7 to 13 degrees, and it's not cooling properly, it's probably not the charge. Heating charge checks. This is always a weird one. I know a lot of guys won't even bother trying to check charge and heating. You should never actually charge the system as if it's going to be finally charged in heating mode. But you can get a good idea if whether or not you are low on refrigerant when the heat pump's operating and heating. So if you can't run it in cooling to check the charge, these are some rules of thumb that you can use to say, okay, does the charge look okay, or does it look like I got a leak? Am I out here because, is the electric heat running all the time because the charge is messed up or something else going on? Obviously, you want to try and diagnose any other issues, but if system, worked last summer, everything seems pretty good, but it had a slow leak or something, and you want to check and make sure the charge looks all right in heating. A lot of manufacturers will have heating charge charts. You should use those because they're going to be more accurate than this, but these are generally pretty close. And if you paid attention in that video on what is normal, these things should all make sense to you. So the rules of thumb for estimating if charge is okay in heating are: condensing saturated temperatures are 30 to 40 degrees above indoor temperature. If your saturated temperatures on your condensing side, your indoor unit in heat mode, is not 30 to 40 degrees above indoor temperature, we're not going to be able to give off much heat, right? Our condensing temperature has to be higher than the temperature we're trying to give off heat to. So if it's 70 degrees inside, we should have a saturated temperature in the condenser of 100 to 110. Otherwise, we're not giving off any heat. We can't subcool it before we send it outside, right? Suction saturated temperature should be 20 to 30 degrees below outdoor ambient temperature. Again, if we're talking about trying to pick up heat outside, we can't pick up heat unless the refrigerant is below the outdoor temperature. So you need about 20-30 degrees there to try and get that heat from that 30 degree air outside. So if it's 30 degrees outside, your suction saturated temperature of the refrigerant should be probably about 0 to 10 degrees Fahrenheit. If it's not, then you're not going to be able to pick up any heat. It's not going to do what it needs to do. Discharge temperature approximately 100 degrees over outdoor ambient. That's the only one that you can't go by the what is normal to figure it out. but it's basically just saying you're picking up heat and you should be close to what you're trying to get inside. Um, Systems that work better in low ambient, your mini splits and stuff like that may even be over this. Your green speed systems may even be over this, but your discharge temp is what hits your indoor unit, right? So you need to have a reasonable amount of heat um, to get it to be able to give off that heat in the condenser. So your discharge temperature, that's why you remember the absolute max on your discharge line's 180, right? Well, not your absolute max. The maximum recommended. Generally, you don't want your discharge line to be over 180. Something's going wrong. You don't want to run heat on a heat pump if it's 80 degrees outside, because your discharge temps are going to go high. All right. But generally, they say, and I've never really tested this one that much, but it's a rule of thumb that's out there. 100 degrees over outdoor ambient should be about right on your discharge temp. The first two are what I would use to estimate where my pressure should be, my pressures and my saturated temp. The discharge is just one of those rules of thumb that float around and people seem to think it works. And then your suction line temp, 5 to 15 cooler than outdoor ambient. Again, it should be a little bit lower than outdoor ambient because we're still trying to superheat using that outdoor air, but it should be pretty close. And then liquid line temperature is approximately 3 to 15 warmer than indoor temperature because we're giving off heat to the inside and we're trying to subcool that. So we're going to be 3 to 15 warmer by the time it's all said and done. Anytime your line temp is equal to the ambient that it's trying to give off or pick up heat from, odds are you've got a refrigerant issue there because it's superheating too much or it's subcooling too much. You're probably low on refrigerant there, because you should have basically a little bit of headroom. I don't know how else to put it, but basically you should have a little bit of space there. Unless you've got a gigantic, super efficient coil, there should be some differences between those line temps and the temps that you're in the temps of the air that it's trying to either give off the heat to or pick up the heat from. Does that make sense? All right. So that's your best ways of check and charge. I mean, obviously TXVs are a little easier. Heating charge checks are kind of tricky, but you got some numbers to go off of. Superheat takes a little bit of practice to make sure you're doing everything right, checking everything right. And obviously, if you're really doing a lot of fixed orifices, you should have preferably an induct psychrometer so that you can check wet bulb and dry bulb in the duct. And upside of that is you can perform all kinds of fun calculations if you got an induct psychrometer. But for the most part, dry bulbs will usually get you close enough for most systems that you're going to work with. But there's your ways to check and charge. What was it? Oh, the other thing I was going to say, and obviously, just another note again, and obviously we're going to be talking about troubleshooting these things, so you're going to need all these readings anyway. But if you're charging a TXV system, do not only check subcooling, please check superheat. Always check superheat, because again, superheat is more important than basically every other number. Superheat is what dictates whether or not that compressor is going to stay alive. So if you're not checking superheat, you're doing it wrong. I don't care what other measurements you need to check superheat. Might as well do it while you're there. Catch a problem if it's there. Catch the bad TXV while you're there. Whatever you got to do, always check superheat. Alright, so this is just an example. This will be on the sheet. Again, 75 degrees inside, approximately 50% humidity. Outdoor temperature is 85. You can't see it very well. Hold on. I'll do it like this. A little bit bigger. Let me see if I can and like I said, I'm gonna give you guys, you're gonna be able to pick it up. That's about as big as I can make it. So if that's not big enough, you're gonna have to wait till you put your hands on it. Is it hard to see that? All right. So anyway, if it's 75 degrees inside, 85 degrees outside, you just take your outdoor line, go up until you meet your indoor line that you're working with, and then follow that over so you can get your superheat number. So right here, we're talking about an 8-degree superheat. About 8 degrees of superheat is what you'd be looking for in that situation. So that's how I check superheat. I usually keep one of these pages floating around in case I need it. Or usually you end up looking at the manufacturer's table. But if I'm not sure, then it's an old system, something like that. That's what I'll charge to. All right. Any questions on charging systems? Oh, we're good. All right. So what I was talking about, if the if the in if the what you're saying, hold on, repeat that. If the indoor temperature is low and the outdoor temperature is high. Okay. Okay. If indoor temperature is high, like if you're looking at this chart, right? Indoor temp is high. So let's say it's 95 degrees inside, right? If it's 95 degrees inside and it's 60 degrees outside, your superheat's going to be through the roof. You see that line? So here, I'll even draw a line for you real quick. See, we come up here, right? We're at 42 degrees superheat. So if your indoor temperature is high and your outdoor temperature is low, that is when you're going to have the biggest superheat numbers. So just remember that if you're working on a system where that's the combination of issues you have, you've actually got a low outdoor temp with a high indoor temp. That's when your superheat's going to be high. Basically, anytime your indoor temperature is high, your superheat's going to be high, right? Because you're going to be picking up a lot of heat. But when your outdoor temperature is low, you're going to be feeding a lower pressure to the evaporator coil, right? Since you're feeding a lower pressure, even though you've got subcooled liquid, even if you've got good subcooled liquid going to that metering device, you're going to be delivering it at a lower pressure. Since you're delivering that subcooled liquid at a lower pressure, it's not going to have the oomph, okay? It's not going to have the pressure to push through that metering device. It's got to make its way through that little fixed orifice. If you've ever looked at the holes in those things, they're pretty small. So the pressure is part of what makes it feed enough refrigerant through. So anytime your outdoor temperature is lower, you're going to have higher superheat because you've got less pressure to push through the metering device, even if you've got liquid. Anytime your indoor temperature is high, you're obviously going to have high superheat because you're got to pick up a lot of heat. The more heat you got to pick up, the higher the superheat's going to be. So basically, those two things combine to create a very high superheat condition. And seriously, I mean, it's not uncommon to see, especially plus or minus 5, even if it's 70 degrees outside, right? And it's 90 degrees inside, you might be seeing 40, 45 degrees superheat, and the charger's pretty dang close. The reason I bring it up is, like I said, guys will see something over 20, 25 degrees of superheat, and that's when they start freaking out. Because it's like, what the hell is going on? Why is the superheat over 30 degrees? That doesn't make any sense. Well, it might make sense. You got to pay attention to the conditions where it does make sense. The outlet of the evaporator, ideally, but usually we measure it at the outdoor unit. And the suction line, preferably at the outlet of the evaporator, but as long as you're on the line, you shouldn't have a pressure drop across the line set. So as long as you're measuring it at the, somewhere in the line set, it should be accurate enough if everything else is okay. But if you suspect an undersized suction line or a restriction, if you got a restriction, you're going to have other issues messing up stuff too. But if you suspect a slightly undersized suction line, or you think, like if the suction line's uninsulated and running through a hot attic for whatever reason, and you're not going to fix that right now, measuring it at the evaporator outlet's important. If you're doing retail reach-in coolers and stuff like that, you need to be at the outlet of the evaporator, because everything changes when all those things manifold together. But otherwise, as long as you're measuring superheat somewhere in that line set, you should be fine. 95% of the time. Anything else? Good. All right. So now the fun stuff. Let you measure subcooling, the outlet of your condenser, where you hook up your gauges. So if we're talking residential splits, I don't know what you work on a lot. We're talking residential split systems, right? Where you hook, generally wherever you're going to be hooking up your gauges is where you're going to end up measuring subcooling and superheat, unless you got a weird situation. But you should always measure subcooling at the outlet of the condenser, because that's going to be the most accurate spot, and superheat at the outlet of the evaporator, because that's going to be the most accurate spot. But as long as you're within the line set, you're fine. Subcooling is the same as superheat. You just take your pressure, check the line temp, and calculate your subcooling. Alright, so let me switch to this Excel sheet. Alright, let me... So, I don't know if you guys have ever seen Carrier's charts. Maybe, I wonder if I can bring one in real quick. What's up? Yeah, I will make this a PDF and put it in Google Classroom. So, trains. If I was trying to figure out if I can pull something up. Let me pull this up real quick. Give me just a second. Matter of fact, while I'm let me present the browser. Give me just a second. I'm gonna stop presenting for a minute. See if this works. Alright. I'm presenting my internet browser, so you guys should see you. But if we go here, can you guys see the browser where I'm at? Can you see the URL and all that stuff? Alright, so if you've never been there, if you guys have never been there, if you go to cematraining.com, alright, for those of you by Carrier, you may already know about this, but if not, there you go. There's another good resource. If you don't sell Carrier, you might not know it's there. But cematraining.com is Carrier Enterprise Mid-Atlantic technical support site. So, Train's got a lot of good books so far. Well, no, they got a lot of good PDFs online too. I can't say that, but it's a little harder sometimes to find Train's troubleshooting resources. Goodman's are usually easy to find. Some of Goodman's stuff is pretty good, but it's not as in-depth. Carrier Mid-Atlantic has troubleshooting resources right on their website. So if you got to work on any of their green speed stuff or something like that, you can find the information here. They change these forms a little bit, but a lot of times this is what the chart will look like. Everybody see this quick system analysis chart? All right. So this quick system analysis chart is how you'll see a lot of charts made up for troubleshooting issues in refrigeration systems, and they work pretty good. Um, I never liked Carriers that much. I always liked Trains a little bit better out of their books. But this is kind of what I'm showing you guys now is, and I'm going to switch back to that. But it's basically just this, going over all the issues you could have and what your pressures and temps are going to be. So the thing is Carrier and Train like to add discharge pressure. They like to add amps, and they like to add just other stuff. Discharge pressure, amps, and then what's the other one? I think one of them adds discharge temp. They'll tell you what the discharge temp is or whatever, and I just never found it helpful. 9 times out of 10, this is all you need to troubleshoot it. As long as you got head pressure, subcooling, suction pressure, superheat. Now, you need to know what outdoor temps and indoor temps are to determine whether or not these are low or high or whatever. So you still need indoor dry bulb, hopefully indoor wet bulb, outdoor dry bulb, return and supply on outdoor, condenser in and out on outdoor. You still need those ambient temps, right? Because that's what tells you whether or not they're low, high, normal, what. But other than that, as long as you know if head pressure is low or subcooling is low or suction pressure is low or superheat's low or whatever, that will usually be enough for you to determine most of the problems out there. And the ones that won't help you determine are probably going to be ones where you've got a couple problems together anyway. So in general, if the system's not removing very much heat, your compressor amps are probably going to be low. If the compressor's working hard and it's a hot day, your compressor amps are probably going to be high. If your condensers, if you got low airflow through the condenser, your compressor amps are probably going to be high. Your discharge pressure should generally be the same as your head pressure anyway, unless you got a problem in your condenser circuit. Those are relatively rare. Rare enough that I don't think you need to be taking discharge pressure or looking at it in a chart all the time. You'll get used to this stuff anyway, but this is what you need for 95 to 99% of cases. So I kind of like it just laid out a little more simple. If you guys have never seen the one in back of Ari Michael's catalog, it doesn't even give you this much. It just says head pressure, suction pressure, superheat, what you got, and how those low or high, and their charts based off of that. But this will generally be good for you. So what I have here is, again, head pressure, subcooling, suction pressure, superheat, what they are, then what the problem is. If it's highlighted in yellow, that means those values together help you determine what the issue is. So basically, let's start with the first one real quick, right? The reason suction pressure and superheat and low is in yellow is because, guarantee you, look through this whole line. Do you see anywhere else where suction pressure and superheat is low? There's nowhere. There's nowhere in this chart where suction pressure and superheat is also low. Okay? So that means if you see low suction pressure and low superheat, that is 100% every time. I don't care what you say, is low evaporator heat load. That could be low evaporator heat load because it's low airflow. It could be low evaporator heat load because your outdoor unit is way too big for your indoor unit. It could be low evaporator heat load because they set the thermostat at 42 degrees and it's 60 degrees outside. There's a ton of reasons why it could be low evaporator heat load, but low suction pressure, low superheat is always low evaporator heat load. So basically, if you look at these combinations are what make them special for the most part. Not all of them is that all you need to see to determine if that's the issue, but those are kind of the values that when you see those together, you're going, okay, I've got high suction pressure, high superheat with a low head pressure. I'm talking about a reversing valve or inefficient compressor, because nothing else is going to give me that combination. So that's what the highlight is there for. The other reason it's there is because a lot of times the other values can be unreliable. And there's other instances where I highlighted it where it will be unreliable, but what I'm getting at is these X's mean that it doesn't really matter what values you get there, because the values you're reading don't really mean anything. It could look low, it could look high. It doesn't really matter because those readings could be anywhere. This one where it's low to high, it depends. But these two don't really matter when you've got these two together. So in the condenser subcooling circuit restriction is kind of weird. When we talk about that, you'll get what I mean. But anyway, these highlighted values together are what make that combination whatever it is, essentially. So it's just a way to kind of pick it out a little bit quicker, and you know what values are most important to be looking at it if you suspect. If I suspect the filter's really dirty and that's the problem with the system, then I'll look for low suction pressure and low superheat. If I suspect that it's an overcharge is the problem with the system, then I'm going to look for everything to be high except for my superheat, which will be low. Things like that. So that's what the highlighting is there for. Did I ramble on to that too much, or does that make sense? All right. So this is your quick check. So your quick check chart's right here, and this will just give you a quick glance at what you're looking for. Then when you go down the chart, we'll do each one in particular. And I've got telltale signs here. So if it's not just the pressures that are going to tell you something, if it's not just the temps, then I put other things here that'll help you determine, yes, this is the issue. Then I try to do a brief explanation of why the pressures are the way they are, why the temperatures are the way they are. Going back to thinking mechanically, what's more important than knowing what these should be is knowing why they are what they are. So it's not really that important to remember that low evaporator heat load is low suction pressure and low superheat. It's better to try and know why low evaporator heat load is low suction pressure and low superheat. And we're going to go through those, and then I'll give you some possible causes, some possible solutions. You can almost never do causes and solutions. You can't make it exhaustive. You know what I mean? There's always that weird thing that causes that problem that you don't put in a list. So don't limit yourself to the causes and solutions that are on these sheets, but they're basically the most common and ones you would probably see most of the time. But there's always weird things, and I tried to put as many weird things in here as I could, like stuck check valves and stuff like that you'll probably only see once every 5 to 10 years. But there's still going to be even weirder stuff that you might catch. But at least you've got some ideas of what you're looking for and how to try and fix it. I don't put very detailed information in these solutions, so there's going to be things that we're going to cover later, like troubleshooting components, troubleshooting compressors, things like that will hopefully help these solutions make more sense. Some of them are straightforward, some of them are like, check for non-condensables. Well, how do you do that? Well, we'll talk about it, but I don't want to write that whole procedure in here. If you want that whole procedure, you probably want to buy a service guide that has all this stuff more laid out in it for you. But by the time we're done going over everything in the year, hopefully you'll have all that information. It's just I'm not going to put it all on a single sheet because we might as well write a book then. So we're just going to go through this list in order. let's talk about low evaporator heat load first, and then I think I'm going to take a short break, and then we'll go over the rest. But we're just going to basically go through this list, talk about it. If you guys got questions as we're going through it, something doesn't make sense, let me know. So if you've got low evaporator heat load, what's going on is most people say low indoor airflow because mostly when you see low evaporator heat load, it's going to be low airflow. But if you've got low outdoor temperatures and you don't have very good head pressure control and you're trying to maintain a pretty cool temperature inside, like in a data center or something like that, you could have low evaporator heat load and it be normal. If somebody turns the temperature down way too low on a thermostat, we really can't maintain temps below 55, 60 degrees, and even that's kind of pushing it with an AC system made to cool a house. That's low evaporator heat load. It's not really made to work in those temperatures unless you've got controls to help it do it. So that's the reason I call it low evaporator heat load, but you might just want to think about it as what you're going to normally have. That's misspelled anyway, so fix that. You might want to just think about it as low airflow, because that's usually what it is. So if you got low evaporator heat load or low airflow in the evaporator, it's always low suction pressure, low superheat. Low suction pressure with low superheat is always low evaporator heat load. There are no other refrigeration circuit issues that cause both these numbers to be low. The pressures are low because the superheat is low. The superheat is low because the system cannot pick up adequate heat, either due to low airflow or operation outside of design conditions. Subcooling is irrelevant and inaccurate due to the low head pressure. Because our head pressure is low, you're probably going to have low subcooling, but if you've got low evaporator heat load and it's hot outside, you might have normal to high subcooling. It's hard to tell sometimes. But it's irrelevant. It doesn't matter. Your head pressure is definitely going to be lower than normal, and your suction pressure and your superheat are low, and that's the two most important ones. The bad thing about low evaporator heat load is it makes a vicious cycle, right? Your superheat's low. Since your superheat's low, you're probably going to start creeping towards freezing. If you actually hit freezing as your superheat and your suction pressure drop, right? If you actually hit freezing, then you start to form ice on the coil. You start to form ice on the coil, and you start to get even less airflow because the ice is taking up space on the coil. So that makes your superheat even lower to non-existent, which helps form more ice, which causes lower airflow, which makes it worse and worse and worse. One of my favorite examples, and we'll probably talk about it in again with duct sizing, is we did a building one time where it was basically... it's a long story, but it's basically a 20-ton outdoor on a 10-ton indoor. Okay. When you see that, everything seems like it's working fine for like the first hour. And then after 4, 5, 6, 7 hours, you just see that suction pressure and that superheat just slowly die because it just keeps going and going and going until it finally all freezes up and it ain't working. So, I mean, just slightly low airflow, 325 CFM per ton can throw you in that vicious cycle sometimes. Now, I will say this, though. My experience has been, and this isn't all the time, but it's most of the time, if you've got low evaporator heat load because of a dirty filter or something like that, or a damper's closed that shouldn't be closed, or whatever the case may be, if it's frozen up when you get there, and the filter's dirty or something like that, you thaw it out, throw a new filter in. Don't necessarily call it good, because my experience has been that if the system actually freezes up into an entire block of ice, it's usually a combination of low airflow and probably a slight to reasonable undercharge. So it's not all the time. There are plenty of times when it's just the filter's completely packed, or the filter's completely packed and the evaporator's dirty as hell, or whatever the case may be. It doesn't mean it doesn't happen, but I've just had it happen too many times. I've had to go back too many times on what you thought was just a dirty coil, and you didn't check the charge after that or something, and it turns out that it's also undercharged. So if the coil becomes a complete block of ice on the inside during AC season, check charge and low airflow. Check both, because it can be one or the other, but it's usually both. Because if you're just low on charge, you should have high superheat. You shouldn't start freezing. If you're just low airflow, but your charge is good, a lot of times the suction line will still end up staying above freezing for a reasonable, at least long enough that it'll cycle a little bit or something will happen and it won't turn into a block of ice. So just keep it in mind. Always check for both when you have a completely frozen coil. So again, causes could be indoor set point too low, could be dirty filter, could be dirty blow wheel, could be the wrong fan speed. Always double check the fan speed. The guy behind you didn't necessarily do it right. All right, undersized ductwork. The discharge line? What do you mean the discharge? You mean the liquid line? So the suction, well, that's not a discharge, right? So the suction line is frozen from the in. Right. Yeah. It's low evaporator heat load almost every time. It's almost always low airflow. It might be an undercharge. It might just be an undercharge, because it does happen if your charge is just right, okay? If your undercharge is just right so that your suction's running right at about 32, you might have that happen, okay? I've seen it, I want to say, once or twice. But it's almost always something wrong on the the airflow side of the evaporator, because that's what causes the line to freeze. Well, I'm trying to tell you. No. I'm trying to tell you right now, right? So these are the possible causes. Indoor set point too low, right? That could be the issue. But 9 times out of 10, it's going to be wrong fan speed, undersized ductwork, block vents and returns and closed dampers, or dirty filter or dirty coil. I didn't even write dirty coil on here. I'm going to put dirty coil next to dirty filter. All right. So those are probably the problems that cause your suction line to freeze up all the way out to the outdoor unit. The solutions to that are: check the cleanliness of all your system components first. Remember, if you suspect a problem in the system, the first thing you should be doing anyway is checking that your filter's clean, your coils are clean, your blower wheel's clean, everything looks good, because you can't diagnose anything if all that stuff's wrong. All right? If the evaporator's frozen, so you get there and that whole line is frozen and the evaporator's frozen, the first thing you have to do is thaw it. Can't do anything else to the thing thawed. You can't diagnose it while you got no airflow. Make sure the indoor set point's not super low. Check proper fan speed. Check the unit to make sure this fan speed is set to manufacturer's recommendations based on the static pressure that you have in the system. If you're unsure, just set it on high. That's what most guys do anyway, set it on high. That's not always right. It's right more often than not these days, but set the evaporator on high if it's on a different speed, and see if that makes any difference on the airflow that you're getting. Check your return and supply duct size. We'll learn later this year how to properly check the size of the supply and return ducts, but you need to check and make sure the size properly. You need to make sure the filters are sized properly. It's another thing, the filter's really dirty, so you get low airflow. Well, really dirty filters are usually because of undersized filters. So it could be that the filter's been undersized the whole dang time, and that's a big part of the problem. Check all your returns and supplies have dampers open, including the registers. They can't block return ducts. I don't know how many times I've walked in, people got half their diffusers blocked off, and some guy told them they should block off the return in the basement or some stupid crap like that. You can't have any vents in the system blocked off. If you want to close 1 or 2 in a room, that's fine. If you're going to close 6 or 7, yeah, you're probably going to have problems. And then, of course, Again, I didn't put it here, so I thought it'd be self-explanatory, but maybe it's not. But if that fails, clean all the system components, and then check for system mismatches. You know, it could be that the outdoor unit isn't compatible with the indoor unit. But those are the things you have to do to check it. I will tell you, if that happens, 9 times out of 10, it's going to be a dirty coil. It's usually what it's going to be. That's what you should do, clean the coil. That doesn't mean it's always what it is, though. You need to know the other things it could be. Does that make sense? Does that help you out? All right. Any other questions on low evaporator heat load? All right, so I want to take like, I don't know, 5 minutes. Absolutely, just straight 5 minutes. At 8:05, I'll start back up and we'll go through a few more of these. If not most of them, we'll see if we can get through all of them. Alright, so, oh, wait. Mike would help. Alright, so if we keep going, next issue we could run into is an undercharge. Next one on our list anyway, right? On an undercharge, head pressure is going to be low, subcooling is going to be low, suction pressure is going to be low, superheat is going to be high. You have to take all those into account to determine if you got an undercharge. All right, all those are going to be important values. System pressures and subcooling will be low, often very low, and there will be high superheat. If the system is left off, refrigerant saturated temps may be below ambient. That usually indicates an almost flat system. I mean, you might have a pound left in it, depending on obviously how much it holds. But typical residential system, you might have a half pound left in it. But if you ever have the system off, it's just sitting there for a little bit. It's 80 degrees outside, and you take the pressures, and your pressure is at 60 degrees saturation temp. Then your system's low on charge, okay? Because anytime it's been off for a little bit, whatever ambient is should be what the saturated temperature of the refrigerant is. So if the refrigerant saturated temps are below ambient, if the system is left off, then you're probably low on charge. And when you turn it on, you should see everything's low except for your superheat's going to be high. One thing I didn't address, I meant to address this at the beginning, so let's talk about it now real quick. Alright, so all these are based on a fixed orifice. If you have a TXV, it's going to be the same. But the thing is, on a TXV, the TXV is going to adjust to try and fix these values. So if you've got an undercharge with a TXV, head pressure is going to be low, subcooling is going to be low, suction pressure might be low to normal, superheat will be high to normal. Everything on suction side is going to skew towards normal with the TXV. So if it's a slightly low charge, everything might look fine. You just have your slightly low head, and a low subcooling. If you're really low on charge, you're still going to have these same values on a TXV. Everything is going to be low, and your superheat's going to be high because the TXV can't open enough to let enough refrigerant through. So it's going to basically behave like a wide open fixed orifice at that point. But the bottom line is most of these problems, if it affects the suction side, the evaporator side of the system, if you have a TXV, a TXV might skew the readings towards closer to normal. So you got to be a little bit more wary of what the TXV is doing if the TXV is hunting. Probably, I think next Tuesday will probably be the class where we cover TXVs, if I had to guess. But just remember, for all these charts, TXVs may help skew it to normal if it affects the suction side of the system. If it doesn't affect the suction side of the system, if it doesn't affect superheat or suction pressure, then it won't matter that you have a TXV. But if it does affect that side of the system, it may skew towards normal, and it may not be quite as obvious that the suction pressure is low and the superheat's high. Anyway, the reason the pressures are low is because inadequate refrigerant in the system, and therefore there's inadequate energy available to bring the system to design conditions. We can't pick up enough heat. We're trying to pick up as much heat as we can. We're picking up all the heat in the world, but it's still not enough heat. We're not raising the pressures up, so everything stays low, and our superheat's high because we've got enough refrigerant to superheat the heck out of it, but that's all we got. We just got enough refrigerant to keep it, to pick up what's there, basically. A lot of times that suction line, if it's low, that suction line is going to be close to indoor ambient. So, you'll have a suction pressure of, 35, 36 degrees, but the suction line temperature is going to be 75 into 75 inside. It's going to be close to ambient because that evaporator is starved for refrigerant. It's picking up all the heat it can, and it can't pick up enough heat to bring everything up. Superheat is high because the evaporator is starved for refrigerant. Anytime we say the evaporator is starved, it just means there's not enough refrigerant in there to provide enough cooling. So causes for undercharge are pretty easy, right? It's either improper charge or there's a system leak. It's got to be one of the two, pretty much. There's not many other things that are going to lead you to an undercharge. Either they didn't charge it right in the first place, or it's leaking out. So the solution is look for signs of leaks, look for oil, look for a reason, look for things that are leaking. If you don't see signs of oil or anything like that, then suspect maybe they just didn't charge it right in the beginning, or someone could have stole some refrigerant out of it. I guess I've never actually seen it happen, but they say it happens. So you know those are the issues you're looking for. Charge system, and observe the pressures rise. If a refrigerant is added and the pressures do not rise or superheat does not fall, check for other issues. I put another note in here. Always use a scale while charging. If full calculated weight of system charge is added and the problem persists, then stop and check for other issues. So some things, a lot of guys see high superheat, they assume low on charge. You shouldn't assume low on charge just because the high superheat or the low suction pressure. That's how low evaporator load gets turned into an overcharge. A dirty filter can get turned into an overcharge real quick if you're not checking superheat and you're just checking pressures. But anytime I charge a system, and I think it's a pretty good habit, right? Anytime you're charging a system, just go ahead and pull out a scale. Throw the cylinder on the scale, charge the system, and watch for everything to become normal. Look at the side of the system and just see what the condenser calls for. I don't even care if you calculate line set. Unless you've got a 150-foot line set, odds are if you just weigh in condenser charge, you'll get close enough that things should start looking normal. So if that system says it holds 5 pounds of refrigerant and you add 5 pounds and this stuff's not changing, it wasn't an undercharge. Stop. Go back, pull out what you put in, recover it so that you can weigh it back in and calculate it with the line set and put in a proper system charge, and then figure out where your diagnosis went wrong. But it's always a good habit, if you think there's an undercharge, pull out your scale while you're weighing it in and look for, okay, things are starting to get normal. If things aren't starting to get normal as you weigh it in, you just misdiagnosed it and you need to figure out what's going on. Or if you start charging it and your head pressure starts shooting up real fast, it was low and now it's just climbing like a rocket, then you probably weren't actually undercharged. You need to figure out what else was going on, because you probably just had a misdiagnosis. But undercharge is pretty easy other than that. Just don't let other things that cause high superheat or low suction pressure to trick you into an undercharge. Make sure everything else looks low and you got high superheat. Odds are you're undercharged, and then look for that refrigerant saturated temp to be below ambient. That is really your telltale sign of a real undercharge. And a lot of times by the time you get to an undercharge, it's 2, 3, 4 pounds low, something like that anyway, because it'll usually work just enough they don't call you till it's a good few pounds empty, and you'll see the undercharge pretty quick if that's what it is. Any questions on an undercharge? All right, liquid. No. I sent you one with a diagram telling you what normal pressure should be, but I haven't put this. What you're saying, you want the sheets before we do the class so that you can go over it during the class? Yeah, we can do that. It's a good idea. I like it. So I will try to put these up beforehand if possible. Now granted, I'm usually last minute trying to put all this stuff together to get it to you, right? So it might not be able to happen every time, but I'll try. Like this, I probably could have put up last night if you guys wanted to look at it before we started. So for this particular class, look through it after class or tomorrow or whatever, and then if you got questions, you can go through it Thursday, and then obviously you can watch the video if you want to see what I said on something again, because I should have that up tonight. I'll probably edit out some of the blank spots, but other than that, I should have it up tonight. Yep, good idea. All right, liquid line restriction. Liquid line restriction and a failed metering device look exactly the same for the most part. So these next two, you're going to see almost the exact same diagnostics. The trick is determining which one it is, and the liquid line is the first one you should always rule out. You always rule out a liquid line restriction and then assume you have an issue at the metering device. So a liquid line restriction, you're going to have low to normal head pressure. It depends on how big the restriction is, what your head pressure is going to look like, but it should generally be low, but it might look semi-normal. Your subcooling will be high. Your subcooling's high because you got a restriction, so it's going to back up more refrigerant in the condenser. So subcooling will be high, suction pressure will be low, and then superheat will be high. So the telltale signs of a liquid line restriction is high subcooling and high superheat. If you have a high subcooling and high superheat at the same time, it's either an issue in the liquid line or an issue at the metering device. For a liquid line restriction, the real sign is a 3 degree or greater temp difference across the liquid line. So if you measure the liquid line temperature at the exit of your condenser and then at the inlet of your metering device, basically, go from your condenser all the way to your metering device. If you have a 3 degree difference in the temperature in that liquid line, then you have a restriction in it. If there's no temperature difference, then the problem's probably at your metering device. So subcooling is high because the liquid is being backed up into the condenser. Head pressure will be low to normal because of the very high subcooling. So even though we're backing up, you think the pressure would build a lot. The only reason the pressure doesn't build a lot is because we're subcooling so much. So a lot of times that extra subcooling will keep the head pressures from going as high as you think they might with a restriction. You automatically assume, you close off the line the compressor is going through, and that's going to cause a really high pressure. But usually it's not completely closed off, and the subcooling kind of skews those pressures downward. The superheat is high and the suction pressure is low because inadequate refrigerant is entering the metering device. Or entering the evaporator. So I actually don't have enough space for that. Need to fix that. Another good thing about going through this together, can fix the issues before you tell me I got a bunch of problems when I make it a PDF. Alright, causes for the liquid line restriction are undersized liquid line. So if you're supposed to have a 3/8 liquid line and you got a 1/4 inch, that's a restriction. Clogged filter dryer is kind of your most common, and then your kinked or your damaged liquid line is the next most common. So the solution is check for the delta T across the liquid line from condenser evaporator. If you got a 3 degree or greater difference, check across the filter dryer. Isolate sections and components that you have in the liquid line until you figure out, okay, where's it at? Is it in the line set between the where it goes in the house and the evaporator, where it's inside the wall? Did it get kinked there? Is it right there at the filter dryer? Is it somewhere else? Try and isolate sections until you figure out where that 3 degree temperature drop is happening, and then check that the liquid line is properly sized. If the issue is the filter dryer, obviously replace the filter dryer. That's your most common issue, is a clogged filter dryer. If you got a liquid line restriction, and like I said, the next one would be you just got a kink in the liquid line and you got to cut that piece out and put a new piece in. If you check across the liquid line and you do not have a liquid line restriction, then you have a failed TXV or a failed metering device in some way, shape, or form, or the inlet screen to that metering device is restricted. So we'll have the same problems as a liquid line restriction: low to normal head pressure, high subcooling, low suction pressure, high superheat. The telltale sign, though, is the high subcooling with the high superheat but there will not be a 3 degree or greater delta T across the liquid line or filter dryer. So it means it's not in the line set. The issue is in the metering device itself or at the inlet screen of it. So the subcooling is high because the liquid's being backed up in the condenser. Head pressure is low to normal because of high subcooling. Superheat is high, suction pressure is low because the inadequate refrigerant is entering the evaporator. So that is that's what that is. So the causes of that are loss of charge in the sensing bulb that will cause a TXV to close completely up, and it cause a liquid line restriction. An undersized metering device, you're supposed to switch out the metering device when you need to on when you got a piston. You need to make sure the piston is matched to the outdoor coil. If the piston is the wrong size, then it will act as a restriction. Could be a clogged inlet screen at the TXV or the piston or fixed orifice. So almost all metering devices, you're going to have a little inlet screen there right before it. So if you suspect the issue with the metering device, usually you're going to bring a new metering device with you anyway. Install the new one just to cover your butt by the time you vacuum everything out, to make sure that by the time you pump it down and get ready to put a vacuum on it, the cost difference of a new metering device versus no new metering device isn't enough to worry about. But if you're pretty sure the metering device is fine, or you've got a piston, you could be able to just clean out the piston or clean out the clog in the inlet screen, and you'll be good to go. So just look for, if they didn't purge while they're brazing, and you got a bunch of black stuff in the inlet screen, if you clean that out, it'll probably be fine. And moisture freezing at the metering device. This isn't really the same thing. This is a whole nother issue, but it could cause a similar looking problem. So just keep that in mind. If you have moisture traveling in the system, you got no filter dryer, you've got basically droplets of moisture traveling through the system, they can freeze up right at the metering device and make it look like a liquid line restriction. So just keep that in mind, but usually you'll see other things that will tell you that it is not the metering device, that it's moisture. Solution is first verify the issue is not in the liquid line, pump the system down, remove the inlet screen and the metering device, and inspect them. Clean and reinstall or replace. If it's a TXV, replace the TXV if no debris is found in the inlet screen. Probably just replace the TXV anyway. If you got a failed TXV, I've seen them where they're only kind of failing, but you got high superheat and good or high subcooling, just replace the TXV. If superheat's too high, replace it. If superheat's too low, replace it with the TXV. Anytime you've verified that the issue's at the TXV, just replace it, especially if it's non-adjustable. If it's an adjustable TXV, you might be able to adjust it, but most of us deal with non-adjustable TXVs. If it's an EEV, if it's an electronic expansion valve, consult manufacturer's instructions to troubleshoot the electronic components of the EEV. Replace it as necessary if there's no debris in the inlet screen and proper signal is being sent to the EEV. Next one is an oversized or overfeeding metering device check valve, or check valve stuck open. So if you get no metering device in there, and this actually happened to me not that long ago, so it happens, right? You got no metering device in there at all, or the metering device is too big. You got a 5-ton TXV on a 2-ton system, or you got a giant piston on a smaller system, or the TXV's stuck open, or some systems have the check valve around the fixed orifice or the TXV. If it's a cap tube, they'll have a check valve around it. That check valve might be stuck open, so it's not metering. If you have any of those issues, the signs of that are going to be a low head pressure, low subcooling, but it's really irrelevant, high suction pressure, and low superheat. Basically, anytime you got low head pressure and high suction pressure, you've got a small group of problems that you can have, because it's not very often you have low head with high suction. It's kind of hard to pull that off. So you got a very narrow group of about 3 problems you're usually looking for. And the way to know that this is this is an overfeeding issue and not something else is that the superheat is low. So if you got low head with high suction but a low superheat, then you've got too much refrigerant moving through the metering device somehow. You got to figure it out. So again, telltale signs are low head pressure with high suction pressure and low superheat is an overfeeding metering device or a check valve stuck or something similar. Other issues with these two systems usually have a high superheat. So head pressure is low and suction pressure is high because too much refrigerant is entering the evaporator. Subcooling and superheat are low because refrigerant is essentially traveling too fast to facilitate any heat exchange. It's just circulating through the system super quick because there's nothing slowing it down. So it's coming out of the compressor and basically going right back to it. So you're not exchanging any heat because you're just feeding too fast. That refrigerant's moving through that system way too fast. So the causes can be oversized metering device, no metering device, overfeeding or failed open TXV, which does happen sometimes, check valve stuck open, piston not seating properly, or the TXV sensing bulb. Probably the most common way you'll see this issue is somebody didn't mount the TXV sensing bulb right, and so it's reading a higher heat than it should. Anytime you need that TXV to feed more refrigerant, you hold that sensing bulb in your hand, right, and warm it up. So if that sensing bulb gets warm, it's going to feed more refrigerant. So if it's not installed properly, that TXV is going to overfeed. Solutions are pump down the system, check for signs of an inefficient compressor, because that's the other issue it could be. But it's probably not, because that's usually high superheat. Check TXV sensing bulb for proper installation. Remove a metering device. Check that it's properly sized. Ensure that there's a temperature difference across the check valve. If there's check valves in it, make sure that it's not stuck open. If you're reading the same temperatures on both sides of that check valve, it's stuck open. If it's supposed to be closed and it's not, then the check valve's bad. And then the next thing is just replace the metering device, which is generally what you're going to be doing. You're either going to be fixing where the sensing bulb is at, or you're going to be replacing a metering device, or installing a metering device for the first time. Reversing valve, bypassing hot gas to suction. So these next two are the other things that will give you a low head pressure and a high suction pressure, but they have high superheat. Okay, so if you got low head pressure and a high suction pressure and low superheat, you're feeding too much refrigerant. But if you've got high superheat, then you've got a reversing valve issue or an inefficient compressor issue. If you're not working on a heat pump, then it's probably the compressor. If you are working on a heat pump, the first thing you want to rule out is an issue with the reversing valve. So low head pressure with high suction pressure and high superheat may be the reversing valve bypassing hot gas. Check for a delta T greater than 13 degrees between the suction at the reversing valve and the true suction going to the compressor. 13 degrees. It's a big temperature difference, but you've got discharge gas commingling right next to suction gas right at that reversing valve. So that suction, doesn't matter what you do, that suction line is going to pick up heat. It's going to. But if you're picking up more than 13 degrees going across that reversing valve, then it's bypassing hot gas. So it's a pretty high temp. Again, generally no more than 3 degrees across any component. The reversing valve is an exception. I've seen different numbers here. I've seen 8, I've seen 7, I've seen 13. I just go with 13 because it's the biggest one I've seen. It's a guaranteed. If it's over 13 degrees, you're bypassing hot gas. It could be less than 13 degrees and you still might be bypassing some, but it's probably not enough to really cause an issue. But if it's over 13 degrees, guaranteed it's causing a problem. So the suction pressure and superheat is high because the discharge gas is entering the suction line. The liquid pressure is low because the compressor is essentially just recirculating refrigerant. So the thing with the superheat being high is the superheat's not really high, right? Well, it kind of is, but it's really not. It's not. The superheat's not high because you're picking up heat from the evaporator. The superheat is high because you've got hot gas going in there, so it makes the temperature of the line hot. So it's not really that the superheat is high, it's just that there's hot gas going in the suction line. So that's why the superheat is high, and it'll usually be really high. Like, you're sitting there trying to figure out how it's 70 degrees inside, but the suction line is 80 degrees high. It'll be really, really high superheat most of the time. So the causes that is damage to the reversing valve body or debris in the reversing valve. Solutions are you can lightly tap the reversing valve with a soft material to free up the slider assembly. So like a soft mallet or another piece of copper covered in a cloth, whatever. You want to tap the slider assembly in the reversing valve, but you don't want to dent the reversing valve, because if it wasn't sticking, it'll be sticking after you put a dent in it. Be careful not to damage the reversing valve body. Run the system in the opposite mode to try and free up debris. So, and the next one is allow system to run and apply and remove power to the reversing valve in an attempt to free the slider assembly. So while the system's off, you can sit there and take the O terminal and just apply red to it on and off. You know what I mean? Jump it, not jump it, jump it, not jump it, jump it, not jump it. Get that slider to try and move back and forth really quick. And then if you let it run, power it in heating or power it in cooling, right? And then take the power off for a couple minutes and then switch it back to cooling. Try and get whatever debris in there is frozen, is freezing up the assembly. Try and get it to move, and you might be able to get it working again. If that doesn't work, you gotta replace the reversing valve. Done. Inefficient compressor is the next thing that'll cause that problem. So if you've got the same issues, low head pressure with a high suction and a high superheat, but you don't have a reversing valve, or you have ruled out the reversing valve, then it is inefficient compressor. And it can still happen with scrolls. And we'll talk about that when we get there. But anyway, telltale signs are low head pressure and high suction pressure with high superheat is generally an inefficient compressor, especially if the system does not have a reversing valve or you've eliminated the reversing valve. Suction pressure and superheat is high because discharge gas is entering the suction line from the compressor or a stuck internal relief. Liquid pressure is low because the compressor is recirculating refrigerant. So, causes damage to the compressor's moving parts. You know, you got especially if it's reciprocating, you got check valves, you got suction valves in there, you have piston rings, you got all kinds of stuff that seal up the parts in there. If they're damaged, it's going to pump gas back the wrong way here and there. Damage from liquid slugging in the compressor can cause the damage to those internal parts. So if you've got an inefficient compressor, always look for what happened to the compressor. Anytime you've got problems with the compressor, the first thing you do is figure out whether or not it's worth replacing the compressor. The next thing you do is figure out what happened to the compressor, because you don't want it to happen again. Compressors don't die, they're killed. Alright, so figure out what's going on there. Or internal relief is stuck open. That's what you're usually going to see on a scroll. And generally it's going to be real noisy. So scrolls don't have valves, right? They have plates. The plates could be damaged, and that can cause an inefficient compressor issue. But the other thing that can happen is that internal relief inside the scroll can get stuck partially open, and it'll just be bypassing gas all the time. So if a system's run with high head pressures for a long time, and that internal relief's constantly opening up and gets stuck open a little bit, the next thing you got is an inefficient compressor. So if it's a reciprocating compressor, perform a pump down test to ensure proper operation. And we'll talk about doing a pump down test at some point, but basically you just pump the system down, make sure it pumps down and holds a pump down. It's not that complicated. If the internal relief is stuck open, you'll usually hear it. I mean, the compressor is noisy as hell when that internal relief is stuck open. So hopefully you'll be able to just notice it from the sound. But if not, you just diagnose it and replace the compressor, because either way it's an inefficient compressor. Replace the compressor, check for causes of the previous compressor failure. condenser subcooling circuit restriction, or a backwards heating piston. So backwards heating metering device. Alright, so I've only ever seen this once, and that's what it was, the backwards piston and heating, because it was double metering basically. But the other thing it could be is a kink in the subcooling line of the condenser. So if you don't know, the last circuit in a condenser, the very bottom circuit, all the refrigerant goes through. All the refrigerant gets distributed to multiple lines inside the condenser, and then they come back together. Then they go down, and they all together go through the last loop of the coil, basically, and that's the subcooling circuit. So that's the very last spot before you exit the condenser. It's the very last part of the circuit. And if that's restricted, or you got a metering device on the outdoor unit as it exits the subcooling circuit, then you can have a restriction there, and it'll cause a problem. What you're going to see is low head pressure, and you'll have low to doesn't make no sense to super high subcooling. Okay, it all depends on what you have. So the only time I've ever actually seen the issue with the backwards piston, your backwards heat piston, the subcooling was like 60 degrees or 50 degrees or something ridiculous. The telltale sign is subcooling may seem very high, but the reading's inaccurate. It doesn't mean anything. That's kind of your sign isn't even related to the subcooling, but it kind of is. It's the liquid line temperature being below outdoor ambient is your telltale sign. So if the liquid line temperature, remember we talked about this, that liquid line temperature cannot be below outdoor ambient temperature. So if it's 80 degrees outside, all right, if it is 80 degrees outside, that liquid line cannot be 70 degrees. Can't happen. It's not possible. Not unless you got water on the coil. Then let the coil dry up and verify it's still the same. But if it's 80 degrees outside and that liquid line is 70 degrees, something's going on. There's some kind of restriction, because you can't make 80 degree air make refrigerant 70 degrees. It doesn't work like that. Okay? So that's really what you're looking for. You're looking for the low head pressure. You're looking for generally awful cooling performance, right? Because you're restricted, right? You basically got a liquid line restriction before you even hit the liquid line. So you're going to get crappy cooling performance. You're going to have low head pressure, and usually you're going to end up with a liquid line temperature that is below ambient. Head pressure is low because there's a restriction preventing refrigerant from traveling to the liquid line. Subcooling will be low or very high. Suction pressure is low and superheat is high because the evaporator is starved. Causes a backwards outdoor piston. Damage to the condenser subcooling circuit, or debris in the condenser circuit. Solutions: pump it down, recover refrigerant, and ensure the metering device is installed properly. If you've got an outdoor TXV, make sure that it's operating properly. All that stuff, but make sure that metering device is good and it's working. If the metering device is good and it's working, replace the condenser or that section and piping or whatever you need to do. But generally it's going to be, when you see this issue, it's usually going to be something to do with either the valves exiting the condenser, the metering device for heating, or somebody put a big old dent in that condenser, and it'll probably be hard to miss. Suction line restriction. Suction line restriction is tough. Suction line restriction usually just looks like low charge. Suction line restriction is one I want to play with and see if I can get some results that'll help us figure it out. But a lot of times the suction line restriction's a head scratcher if it's not obvious, and it's obvious when you have a suction line dryer. If you don't have a suction line dryer, it's a weird one if you can't see the restriction. But you're going to have low head pressure and low suction pressure. You're probably going to have low subcooling, and you're probably going to have high superheat, but it could be, depending on where you measure it, it could look like low superheat, could look like really low superheat. But the problem is because the suction line's so cold, the suction line is colder than the indoor temperature. You can't say, oh, well, it's below ambient, so we're going to, I got a restriction. It doesn't really work like that, so it can be a toughy one to find sometimes. But basically, your subcooling, your superheat's irrelevant because the temperatures, you're not going to know what they should be, especially the superheat because there's a restriction in the line. So basically, the only real way to tell is a 3-degree or greater temperature difference across the suction line or the suction line filter dryer. If you got that temp difference, then you definitely have a restriction, but it's going to be hard to tell for sure if otherwise. So basically, just if you have weird problems, like if it looks like an undercharge and you try and charge the system and nothing seems to be fixing it, you know what I mean? You add charge and everything's still kind of low. None of the pressures are really moving right. It doesn't look right. Check your line. See if you got a greater than 3-degree temp difference. See if the suction line's grossly undersized. See if they put a 3/4 liquid line on a 5-ton. You know what I mean? Look for weird things like that because you could have a suction line restriction. The pressures are low because there's not enough refrigerant getting back to the compressor for it to provide enough flow throughout the system. Subcooling and superheat would just be inaccurate. Kinked or damaged suction line or a clogged suction line dryer or an undersized suction line are going to be your problems. Solution is check for delta T across the suction line and any components in the suction line, and to check if it's properly sized. So that's your, if you get that weird one day where you thought it was undercharged but it's not, double check that. Everybody still good? Everybody can hear me? We even got like everybody in here. All right. All right. So yeah, let's go through. What do we got left? Yeah, we can get through this real quick. We can get through this real fast. All right. High evaporator heat load. So basically, it's hot as hell inside, and you got to cool it down. So high evaporator heat load should be pretty easy. High head pressure, normal subcooling, high suction pressure, high superheat. So everything's high, but your subcooling should be normal. Now on a fixed orifice, what's normal, right? It's hard to, there's no charts that tell you what your subcooling should be on a fixed orifice system. But basically, everything's just high, but it doesn't look like an overcharge because you don't have low superheat. Okay, so if everything's high but your superheat's high, your subcooling, but it doesn't look, it doesn't look like a dirty condenser. It doesn't look like it's a non-condensables in the system issue, anything like that. Then it's probably just a high evaporator heat load. The telltale signs are all pressures and temperatures are high, but subcooling is normal. Superheat will be high. Return temperatures will be high, but delta T across the evaporator should be normal. So if you got, if it's 80 degrees inside and you got a 60-degree supply, you got a 20-degree delta, it's working. Well, the question is why is the return 80 degrees? You know what I mean? Is it just a high heat load? The system's been off? Is there some other problem? So the head pressures, oh, see, I didn't write this one out. I need to write that one out. So head pressure is high. Head pressure is high because superheat and suction pressure are high. So basically, the fact that we're picking up so much heat is what's driving the system pressures to be high. So because the suction pressure and the superheat are high because we're picking up so much heat, the head pressure is going to be high. Subcooling should be normal. Delta T should be normal. So subcooling should be normal. Subcooling might be a little bit low on a TXV if it's overfeeding refrigerant to try and take care of the issue, but it should be pretty close to normal. It might supposed to be 10 and you're reading 7 or something like that. Again, plus or minus 3, don't start freaking out. But really the reason everything's high is just because you're picking up so much heat. And I guess I can write because you're picking up a lot of heat in the evaporator. So, that's basically all there is to it. The causes of that are unconditioned air in the return is a really common issue, especially ducts in an attic. If the return air duct is leaking and you're getting 100-degree attic air mixing in with your return, then you're going to have high evaporator heat load, and that system's not going to work real good. That's your most common high evaporator heat load outside of they haven't ran the system for 3 days for whatever reason. High temperatures due to system being off for repairs or for whatever reason, or the system's undersized. The system's just way undersized. You'll have a high evaporator heat load on any hot day, basically. So the solutions are to check return air temps and check for infiltration of unconditioned air. Allow the system to run until temperatures drop. Check the system is properly sized for the heat gain. Overcharge. What happened here? I got a feeling that was there before. So telltale sign. Overcharge. Everything's high but superheat low. So all pressures high. Subcooling is high, but superheat is low. So an overcharge, I mean, it really doesn't get any simpler than that. Usually you can spot an overcharge instead of other issues because even though all this stuff is high, because you have the high subcooling, the head pressure isn't that high. I don't know how else to explain it. It's going to be slightly higher than normal. I mean, if they really overcharge it like 4 or 5 pounds, you might get towards you might start getting close to that you're about to trip the pressure switch overcharge. But usually the overcharge doesn't do that because your subcooling ends up getting higher and higher and higher, and that kind of drives the head pressure down a little bit. So overcharge is going to have, like, if your head if a dirty condenser would put you at 400, normal pressures are 200, that overcharge is going to be at 300. It's going to kind of be in between the middle of non-condensables and a dirty condenser and a normal operating condition. It's kind of in between those two. So that'll be high and your superheat's low. So basically that's your last nail in the coffin is low superheat, with everything else being high is an overcharge. So too much refrigerant in the system will cause all pressures to be high. Subcooling will be high, but there's a lot of subcooling. Head pressure will not be very high. Superheat will be low due to the flooded evaporator. Causes improper charging. I mean, period. Too much refrigerant is too much refrigerant. You can't put too much refrigerant unless you didn't know what the hell you were doing. And then the solutions are recover refrigerant until proper operating conditions are met, or weigh it back in. Low condenser airflow will be high head pressure, low to normal subcooling. The low condenser airflow, so like you got a dirty condenser or something like that. A lot of times subcooling's pretty close. The main reason is you got a dirty condenser. It's basically operating inefficiently. But if you got a dirty condenser, and your head pressure should be at 100 degrees sat temp, but the head pressure is at 130 degrees sat temp, but it's 80 degrees outside. You got a 50-degree temp difference. You're still gonna give off heat. Usually, low condenser airflows or dirty condensers don't have very low subcooling, and they usually still cool just fine. Usually the suction side of the system does pretty good, the evaporator side of the system, but you operate with a high amperage and you operate very inefficiently. So that's the biggest problem with a dirty condenser. I actually read an article probably a few weeks ago now where some engineer or something actually said you don't really need to clean your condensers. And I'm not shitting you, man. This I'll have to see if I can find this article. And I mean, it's just an article on some random website, right? But it's still like, who the fuck writes this? But his reasoning, of course, was that the system still functions pretty well, even if the condenser's dirty. Well, yeah, it does, bud, but you're using like 20-30% more energy than you need to. Okay, that's the point. Your head pressure's high, and you're basically making the compressor work harder than it should have to. So why make it work harder than it has to? It doesn't matter that it functions fine. A lot of times dirty condensers are still going to function fine as an overall system, but everything's going to be inefficient, everything's going to be hot, you're going to shorten the life of a compressor and things like that. So there you go, right? Exactly. One of the first times I ever tried to diagnose a failed TXV was actually just a dirty condenser. That's how weird they can look sometimes, right? But because your pressures are so high that you actually get really good subcooling sometimes. But anyway, yeah, it's the point is that head pressure is going to be pretty damn high. Everything else might look low. Everything else might look relatively normal with dirty condenser. Usually it's pretty easy to spot either the failed fan motor or the packed condenser. If you're not sure, try spraying some water through it and see what you get out, 'cause sometimes it looks clean, then you find all the stuff in between the coils. So high head pressure, low subcooling. Subcooling may be close to normal because head pressure and high saturated temperature. Head pressure is high because heat cannot be rejected from the condenser coil depending on how dirty the condenser is or how many fan motors have failed. If it's the only one or it's just 1 out of 4 or whatever, the other values may be close to normal. Cause a dirty condenser fan failure, clean the condenser coil, correct the condensing fan failure. That's pretty much what it boils down to, right? And then the last one we will talk about is non-condensables. Non-condensables, you will have a high. A lot of times it's a very high, but it may be fluctuating between normal and high, but you will have a high head pressure. And the trick here is the fluctuation, because usually you'll see a fluctuation. Telltale sign is usually high to very high head pressure. Pressures will generally fluctuate. Gauges that are not flutterless may flutter. So if you ever pay attention to specifications on analog gauges, especially from like Yellow Jacket and your bigger companies, they'll say it's a flutterless gauge. Flutterless gauges are nice because they don't flutter on you. But I'll tell you what, if you need to diagnose non-condensables and you got a flutterless gauge, you'll know it's non-condensables when you hook up the gauge. So it's kind of nice sometimes to have the cheaper one. But anyway, usually I've ran into non-condensables multiple times in a couple different ways. But generally you're gonna see head pressure start at 250, climb up 300, 320, 350, drop back down, go back down, go back up, go back down, and it'll just keep fluctuating. The moisture traveling through the system freezing, or just the non-condensables moving in and out of the condenser essentially. The other thing you may see is super high head pressures. If you got nitrogen trapped in the condenser, basically it just takes up space in the top of the condenser. And I didn't write this down, but I'll try and put it in there shortly. But anyway, if you say you just got nitrogen there, so it's a non-condensable, but it's not really doing anything but taking up space, which is what nitrogen tends to do, it'll all get trapped in the top of the condenser. It'll get and however much nitrogen there is will take up that much space in the condenser. So it basically turns your 3-ton condenser into a 2-ton condenser. Okay, so you end up with a really inefficient, you turn the 13 SEER system into an 8 or 7 SEER system. So you'll end up with really high head pressures if it's just nitrogen in there and you've got a reasonable amount of refrigerant. If it is you've got very little refrigerant and more nitrogen or something than anything else, you'll have almost no compression ratio. Because the nitrogen won't compress, it'll just stay there, and it'll look almost like an overfeeding metering device, but the pressures will be weird, so you'll know that's not what it is. So typically you'll see the pressure fluctuation. If you don't see that, it'll just be super high pressures, and pulling out the charge everything will go wonky when you try and pull out the charge if you think it's overcharged or something. You might clean the coil, and you might try and pull out some charge, and it'll just be your superheat's still crazy high and nothing's seeming to fix anything. And your superheat's usually high, so you shouldn't be confusing it with an overcharge anyway, but it happens. But the really high head pressure and the fluctuating head pressure are usually the signs that tell you got non-condensables. The head pressure is high because the non-condensables take up condenser capacity, essentially reducing the size of the condenser. The pressures will fluctuate as moisture travels through the system, causes our improper evacuation. Pull out the refrigerant, try one more again, because whoever did it last didn't do it. So look for the pressure fluctuation more than anything else. And then if you don't know, how you check for non-condensables in the system is pump it into the outdoor unit, disable your compressor, power your condenser fan. If your saturated temperature does not equal outdoor temperature after about 10 minutes of just the condenser fan running and not the compressor, then the refrigerant in there is not all refrigerant. There's something else. Your saturated temperature, if you pump a system down and get it to the same temperature as outdoor ambient, your saturated pressure, the pressure that lines up with your saturated temperature should be the same as outdoor ambient. So if that doesn't work, then something's wrong with the refrigerant. You got to take it out and put new refrigerant in after you've properly vacuumed and changed out your liquid line dryer. And hope there's not a ton of acid inside the compressor, basically. And that's it. That's all the ones I have in here. There are a couple more I was going to put in here. There's a parallel circuit restriction. The moisture traveling in the system I decided to group with non-condensables because it essentially ends up being the same thing. Even though the moisture traveling can look different, usually you're going to have non-condensables at the same time. So these two things are usually hand in hand. And then the condenser parallel circuit restriction, evaporator parallel circuit restrictions and condenser parallel circuit restrictions I've never seen. They drive people nuts when they happen. If a system's driving you nuts, you may want to look for damage to the condenser circuits, the individual circuits, or the evaporator circuits. But basically, if you can't figure anything out, your next best tool is an infrared thermometer. Infrared thermometer will help you find non-condensables if they're stuck in the condenser, because where the refrigerant's not traveling in the condenser, it'll be the same temperature as outside ambient. Looking for circuit restrictions, you'll see the cold section, or you'll see the warm section in the evaporator if refrigerant's not feeding through a couple of those circuits inside the coil itself. Other than that, I mean, they're just not common problems, so I don't think it's that important to throw them in here. If you run into those, you're gonna have fun figuring it out anyway, because you're probably gonna suspect one or two things first. Because who thinks that, oh, they kinked one of the distributor lines? I mean, look for kinked distributor lines, I guess, but I haven't ran into it yet, and anything I write up is just going to be straight out of a textbook. So if you suspect that, you should probably pull up some textbook and see if it's in there. And that's it. That's the problems we can run into. So the next thing I want to do, how I want to set up these quizzes, is going to be fun. What I want to do is I want to take that sheet that I gave you guys the last class, and I want to try and put some random numbers on it and see if you can figure out what the problem is. That was one of my favorite tests to ever take, and I never could find it. ACHR News put a little quiz out one time that gave you pressures and temperatures and told you to figure out which problem it was. We're going to try and do that, and then I'm going to try and quiz you on it. So that's going to be the next class. We're going to see if we can get through that. That might be really on the fly. So depending on how today and tomorrow goes, what we might be doing is you watching me write that stuff out, and then you guys taking a wild guess at what I'm writing out. Hopefully I've got more time than that and I can plan it. But if not, that's what we'll be doing Thursday. And then we will see if we can quiz you on it, and then we'll move on to probably TXVs and then probably individual components. But if you got any questions on this stuff, look over it tomorrow, Thursday, and then ask me questions on it, and we can go over more particular examples, but for the time being, that's what you're going to see with those individual problems in a refrigeration system. And that's the same any AC circuit. All those things are the same. Doesn't matter. It really doesn't matter if it's a walk-in or a comfort cooling system or a medium temp system. It really doesn't matter. All those things are going to look the same. It's just what's low and what's normal is going to be different. Everybody good? All right, that's all I got. So if you got questions, stick around. Otherwise, I will talk to you guys, text you guys Thursday, let you know what the plan is. And I'll put this stuff on Google Classroom here in a little bit so you can download it in the next couple hours or in the morning. All right, guys. Have a good evening.